Ancient astronomers predicted cosmic events with nothing but stone and sky. Long before modern science, they tracked planetary motions and timed eclipses using methods we are only now beginning to fully understand. This journey reveals their sophisticated techniques, from mysterious stone circles to complex mathematical tables, and how this celestial knowledge shaped human civilization. You will discover how our ancestors decoded the heavens, a story that forever changes your view of history and our place in the cosmos. How did they achieve such precision without any of our technology? And what profound secrets did they uncover about time itself? What does their enduring wisdom suggest about our own quest to understand the universe? Our story begins not with complex calculations, but with the most fundamental of human needs, survival. The first astronomers were not scholars in libraries but farmers and herders watching the sky for signs. They saw how the sun's slow journey across the horizon signaled the coming of spring rains or the harsh, dry season. They noticed how the moon's changing face could be linked to the tides, and how certain star patterns emerged only at specific times of the year. For a community relying on crops, knowing precisely when to plant was the difference between plenty and hardship. This was a science born of necessity, a deep and intimate relationship with the cosmos that was woven directly into the fabric of daily life. Across the open plains, nomadic cultures looked up for a different kind of guidance. They saw in the stars a fixed and reliable map, a celestial compass that could guide them across featureless deserts and vast oceans. The consistent North Star, the recognizable shapes of constellations, these were their landmarks in an otherwise trackless world. This practical observation, repeated over countless generations, slowly transformed into a body of knowledge. It was no longer just about watching. It was about remembering, comparing, and recognizing the grand, repeating cycles of the heavens. This accumulated wisdom found its most enduring expression in stone. Take the great circle of Stonehenge on the English plain. Its massive stones are not placed at random. They align with the sunrise on the summer solstice, the longest day of the year, marking a pivotal moment in the annual cycle. Far to the south, in what is now the Egyptian desert, the even older site of Nabta Playa contains stones arranged to point toward the rising of certain stars, heralding the arrival of vital monsoon rains. These monuments are far more than simple calendars. They are the first permanent records, humanity's initial attempts to build their understanding of cosmic time directly into the landscape. They represent the critical leap from simply observing patterns to systematically recording them, creating a fixed reference point that could outlive any single individual. This was the quiet, patient beginning of a journey that would one day predict the dance of planets and the darkening of the sun. What drove them to invest such immense effort into capturing the rhythm of the sky in stone? And what deeper truths were they trying to preserve for those who would come after? The moon, with its constant waxing and waning, provided the first great celestial clock, but its most dramatic performance was a lunar eclipse, when the Earth's shadow slowly consumed its brilliant face. Ancient astronomers did more than just watch this spectacle. They learned to predict it. They uncovered a grand celestial rhythm known today as the Saros cycle. This is a repeating pattern of eclipses that occurs every 18 years and 11 days. After this period, the Sun, Earth, and Moon return to nearly the same relative positions, and a similar eclipse occurs. To track this immense cycle, cultures like the Babylonians became meticulous record keepers. They inscribed thousands of observations onto clay tablets, noting the precise timing of lunar phases and every eclipse they witnessed. This was not casual stargazing, it was a rigorous, data-driven science. They compiled this information into detailed tables that could project future events with stunning accuracy, sometimes centuries in advance. Their methods were so effective that their eclipse records are still used by modern astronomers to study changes in Earth's rotation. Centuries later, the ancient Greeks engineered a device of breathtaking complexity to perform these same calculations mechanically. The Antikythera Mechanism, recovered from a shipwreck, was a bronze gear train of exquisite precision. Within its intricate workings, specific gears were dedicated to modeling the moon's subtle motions, predicting its phases, and even forecasting the exact timing of lunar and solar eclipses. It was, in essence, an analog computer built over 2,000 years ago. Yet this predictive power was about far more than scientific curiosity. In the ancient world, an eclipse was a powerful omen, a message from the gods that could shake empires and alter the course of history. The ability to foresee such an event granted immense authority. Court astronomers in China and Mesopotamia were not just scientists, they were vital advisors. A predicted eclipse could be framed as divine favor, while an unexpected one could be seen as a sign of a ruler's failing mandate. This knowledge was woven into the very fabric of political power and cultural ritual. How did it feel to possess that secret, to know the moon's next move when everyone else saw only mystery and potential doom? This mastery of the lunar cycle represented a profound leap in human thought. It demonstrated that even the most dramatic celestial events were not random acts of capricious gods, but part of a predictable, mechanical order. By unlocking the secret of the Saros cycle, our ancestors took the first crucial step from simply observing the heavens to truly understanding their underlying mechanics. This hard-won lunar knowledge would become the essential foundation for an even greater astronomical challenge, tracking the perplexing paths of the planets themselves. While the moon offered a reliable rhythm, the sun dictated the very pace of life itself. Ancient builders looked to this daily fire in the sky and sought to capture its most significant moments in stone, transforming entire structures into colossal celestial clocks. From the vast pyramids of Egypt to the stepped temples of Mesoamerica, these architects engineered monuments that aligned with the sun during its most extreme points in the year, the solstices and equinoxes. The Great Pyramid of Giza, for instance, was constructed with its descending passages pointed directly toward the pole star of that era, a fixed point in the northern sky. This was no accident but a deliberate act of cosmic alignment. Across the sea in Ireland, the massive mound of Newgrange, older than both Stonehenge and the pyramids, contains a narrow roof box above its entrance. For just a few minutes at dawn on the winter solstice, the year's shortest day, a single beam of sunlight pierces this opening and travels down a long passage to illuminate the inner chamber. This annual event, a dramatic interplay of architecture and astronomy, lasts for only 17 minutes, a fleeting moment of light in the deepest dark of winter. How did they achieve such precision? Their method was both simple and brilliant. By carefully observing the sun's shifting position on the horizon each day, and by measuring the subtle changes in shadow length cast by a simple stick, known as a gnomon, they could track the sun's slow journey north and south. They noted the 2 days each year when the sun seemed to stand still, the solstices, marking the longest and shortest days. They also identified the 2 equinoxes, when day and night are of equal length. Through patient, repeated observation, they calculated the length of the solar year to within minutes of our modern measurement. This profound solar knowledge was the bedrock of civilization. It told farmers exactly when to plant and when to harvest, ensuring food for the community. It dictated the timing of sacred ceremonies, linking religious belief to the undeniable order of the cosmos. It provided a reliable framework for organizing society, for setting calendars, and for collecting taxes. The mastery of the solar cycle was a monumental achievement, a triumph of human intellect that allowed our ancestors to build their world in harmony with the heavens. Yet the sun and moon were not the only wanderers in the sky. A far more perplexing mystery was moving among the fixed stars, one that would challenge the greatest minds for centuries to come. But the planets presented a deeper puzzle, one that blurred the line between science and the sacred. For ancient priests and scholars, the wandering stars were not just points of light, they were living gods, and their movements were a direct divine language. A sudden comet, a close meeting of planets, or an eclipse were not mere celestial mechanics. They were urgent messages about the fate of kings and the fortune of harvests. This belief transformed astronomy into a sacred duty. In Mesopotamia, Babylonian priests meticulously recorded the heavens on clay tablets, watching for any sign that might foretell war, famine, or a ruler's illness. A planetary conjunction could be interpreted as a warning of an invading army, while the appearance of Mars in a certain constellation might signal a coming plague. The accuracy of their predictions was not just a scientific achievement, it was a matter of national security and a testament to their favor with the gods. Far across the world, the Maya of Central America developed an even more intricate cosmic philosophy. They believed time itself was cyclical and sacred, with cosmic events directly weaving into the fabric of human destiny. Their astronomers, who were also the calendar priests, created elaborate systems like the long count to track vast cycles of time. They could predict planetary movements with remarkable precision, seeing in the steady rhythm of Venus, for example, the pulse of a powerful deity influencing warfare and rulership. This spiritual imperative is what drove the incredible preservation of knowledge. In societies where understanding the sky meant understanding the will of the gods, astronomical data became a form of holy scripture, meticulously copied and passed down through generations of a learned priestly class. Great temples were not just places of worship, they were observatories. Their alignments were precisely engineered to capture the first ray of the solstice sun or the rising of a key star, turning the entire structure into a ritual instrument that connected heaven and earth. The legitimacy of an emperor or pharaoh often rested on this celestial connection. A king who could accurately predict an eclipse or demonstrate his alignment with the cosmic order was seen as truly chosen by the gods. This sacred context, where science and spirituality were one, provides the ultimate explanation for why astronomy advanced so rapidly and so profoundly in cultures that never met. It was the human desire to read the mind of the cosmos, to find order in the chaos, and to secure a place within the grand, divine narrative of the universe. How did this profound union of faith and observation eventually unravel, leading to a new and revolutionary understanding of our place in the cosmos? The planets offered the greatest puzzle of all, their wandering paths a stark contrast to the fixed stars. Night after night, ancient sky watchers from Greece to China meticulously charted these celestial travelers, documenting a behavior that defied simple explanation. Sometimes a planet would slow in its journey, halt, and then appear to move backward against the starry backdrop for weeks before resuming its original course. This backward loop, known as retrograde motion, was a profound celestial mystery. Without our modern understanding of a sun-centered solar system, this apparent reversal seemed utterly illogical. What force could possibly make a divine wanderer stop, turn around, and then change its mind again? The solution they devised was a triumph of pure mathematics over flawed perception. Babylonian astronomers, in particular, turned this puzzle into a computational art form. They recorded their observations on countless cuneiform tablets, tracking the precise positions and brightness of planets over centuries. From this immense archive of data, they discerned repeating patterns and cycles. They developed ingenious mathematical tools like zigzag functions, which modeled the planets' changing speeds, slowing them down and speeding them up in a predictable rhythm. Using these calculated period relations, they could project a planet's future location in the sky with remarkable accuracy, all while still believing the Earth stood motionless at the center of everything. Their models were not physically true in the way we understand gravity and orbits today, but they worked. They were a brilliant mathematical workaround that successfully predicted the dance of the gods. Across the world, the Maya achieved a similar feat with the planet Venus. They saw it as a powerful deity, and its cyclical appearance as the morning star and then the evening star was of supreme importance. Their astronomers' priests created elaborate Venus tables carved into stone that could forecast its appearances and disappearances for centuries into the future. These tables accounted for its complex 584-day synodic cycle, a calculation that required generations of dedicated observation and a sophisticated grasp of long-term mathematics. To predict the behavior of a planet like Venus was to understand the mood of a god, to know when it was auspicious for a new king to be crowned or for an army to march. This was not merely stargazing, it was a high-stakes science that blended precise calculation with deep cultural meaning. The ability of these ancient cultures to anticipate the perplexing movements of planets reveals a computational sophistication that, in many ways, rivaled the astronomy of medieval Europe. They achieved this not with telescopes or physics, but with relentless patience, meticulous record-keeping, and a mathematical creativity born from the need to bring order to the cosmos. They proved that even the most bewildering celestial phenomena could be tamed by numbers, a legacy of prediction that would one day inspire a revolution in how we see our place in the universe. The fixed stars offered a different kind of map, one that charted not only space but also the stories and seasons of human life. While the sun and moon marked the days and months, and the planets told of divine messages, the timeless patterns of the constellations provided a stable backdrop for both practical journeys and profound cultural narratives. For the Polynesian voyagers, the night sky was a living, breathing sea chart. They memorized the precise paths of hundreds of stars, knowing which one would rise directly over a specific island chain. They understood the star compass, a mental map dividing the horizon into sections, each belonging to a particular celestial body. By observing the zenith star that passed directly overhead, a navigator could determine his latitude. They even read the ocean itself, watching the reflection of starlight on cloud banks to sense distant land far beyond the horizon. This was not casual wayfinding. It was a high-stakes science of memory and observation, allowing them to deliberately sail their double-hulled canoes across thousands of miles of open Pacific, settling islands long before European explorers dared to leave sight of shore. At the same time, across the continents, other cultures were weaving the same stars into elaborate tapestries of myth. The Greeks saw heroes and monsters in the sky, like Orion the hunter eternally pursuing the Pleiades sisters. These stories were more than just entertainment. They were mnemonic devices that encoded celestial knowledge. The heliacal rising of a constellation, its first appearance in the dawn sky after a period of invisibility, served as a critical agricultural alarm clock. In ancient Egypt, the yearly reappearance of the star Sirius just before sunrise heralded the imminent flooding of the Nile, the lifeblood of their civilization. This event was so reliable it set their entire calendar in motion, dictating when to plant and when to harvest. Similarly, in China, astronomers had mapped the sky into constellations that reflected their imperial bureaucracy, with stars representing emperors, palaces, and court officials. This celestial mythology preserved vital knowledge across generations, first through intricate oral traditions and later through detailed star catalogues. The very act of naming the stars and telling their stories was a way of domesticating the cosmos, of bringing its vast, impersonal light into the familiar world of human culture and survival. These stellar maps, whether used to guide a canoe to a new home or to signal the time for planting, show us that for our ancestors, understanding the sky was fundamentally about finding one's place, both in the physical world and within the great, unfolding story of time itself. Yet some celestial visitors refused to follow any predictable path, blazing into the sky without warning. Comets were the great wild cards of the ancient cosmos, often seen as portents of upheaval, the death of kings, or the fall of empires. Their sudden, brilliant appearance could send societies into a frenzy of interpretation, but amidst the fear and superstition, a different, more scientific impulse was at work. From the imperial courts of China to the monasteries of Europe, meticulous astronomers were doing something revolutionary. They were writing it all down. Chinese court astronomers maintained an unbroken chain of celestial records for centuries, treating the sky as a divine text that required constant reading. Their observations of what we now call Halley's Comet stretch back to at least 240 BCE, with each return carefully documented, its path across the constellations, its tail's length and direction, and the duration of its visibility. These were not just brief notes, they were precise, data-rich entries in a grand imperial archive. The Chinese saw a clear pattern, noting that certain spectacular comets seemed to reappear after roughly 75 or 76 years. They did not have the physics to explain why, but their relentless record-keeping allowed them to suspect a deep, cyclical order behind what seemed like chaos. This systematic documentation became a gift to science across the ages. When the English astronomer Edmund Halley began his work in the 17th century, he was not starting from scratch. He dove into these ancient archives, compiling observations from Chinese, Babylonian, and European sources that spanned over 2,000 years. By connecting the dots between these historical accounts, he made a breathtaking deduction. The comets recorded in 1166, 1301, 1378, 1456, 1531, 1607, and 1682 were not different objects. They were all visitations of the same celestial traveler. He predicted its return in 1758, and when it appeared right on schedule, it was a triumphant validation not only of his own theory, but of the enduring value of ancient observation. The ability of these early astronomers to predict a comet's return, even if only tentatively, marked a profound shift in human thought. It demonstrated that even the most unpredictable and terrifying celestial events might be part of a grand mechanical clockwork. Their commitment to documentation, a project that spanned continents and centuries, transformed a symbol of divine displeasure into a predictable, orbiting body. This legacy of patient observation reminds us that the greatest discoveries are often built upon the careful, handwritten notes of those who came before, those who looked up at a mysterious light in the sky and chose, first and foremost, to simply write it down. This mastery of the sky required more than just the naked eye. It demanded tools of extraordinary ingenuity. Imagine holding in your hands a device that could map the heavens, tell the time by the stars, and predict their future movements, all without a single electric component. This was the reality for ancient astronomers who engineered the world's first complex scientific instruments. One of the most elegant was the Greek Armillary sphere. A skeletal globe of interconnected metal rings, it was a physical model of the celestial sphere. Each ring represented a fundamental circle in the sky, like the celestial equator or the path of the sun known as the ecliptic. By aligning this handheld universe with the real one, a scholar could visualize and measure the coordinates of any star or planet. Across the Mediterranean and into the Islamic world, this concept was refined into the astrolabe, a portable computer made of brass. Its intricate plates, etched with star maps for different latitudes, could be rotated to solve a multitude of problems. With an astrolabe, you could determine the time of day or night, calculate the hour of sunrise, or find the direction of Mecca for prayer. It was an essential tool for navigation, timekeeping, and astronomy, compressing the vast cosmos into a beautiful, palm-sized disk. But perhaps the most ambitious instruments were those that moved on their own. In ancient China, during the Song dynasty, brilliant engineers like Su Song created colossal, water-powered armillary spheres. Driven by a meticulously controlled water wheel escapement, these great bronze rings rotated automatically, tracking the apparent motion of the stars across the night sky. This was more than an observational tool. It was a working simulation of the universe, a celestial clock tower that merged hydraulic engineering with profound astronomical understanding. And then there is the ultimate enigma, the Antikythera Mechanism. Recovered from a shipwreck off the coast of Greece, this corroded bronze device from the 2nd century BCE reveals a complexity that would not be seen again for over 1,000 years. Through painstaking analysis, researchers have discovered it contained at least 30 interlocking bronze gears. By turning a hand crank, the user could advance a calendar, display the phases of the moon, and even predict the exact timing of solar and lunar eclipses, all displayed on delicate dials on its face. It was a mechanical analog computer, a universe in a box. The creation of these devices reveals a technological sophistication we are only beginning to appreciate. They required not just astronomical knowledge, but advanced metallurgy to cast precise gears, complex mathematics to calculate gear ratios, and visionary engineering to assemble it all into a functional whole. This was the high technology of the ancient world, proving that the journey from simple observation to precise, mechanical calculation began not in the Renaissance, but millennia earlier. What other secrets of their engineering genius have been lost to time, and what might their approach to technology teach us about our own relationship with the cosmos? The night sky itself became a vast, rotating clock face. While grand monuments marked the slow turn of the seasons, ancient cultures also mastered the art of telling time through the silent, steady march of the stars. This was a more intimate knowledge, a skill for priests and navigators who needed to measure the hours of darkness with precision. The Egyptians, for whom the timing of nightly rituals was paramount, used an ingenious tool called a merkit. This simple device consisted of a plumb line and a narrow sight, held by an astronomer who would align it with a specific star. By watching that star cross an imaginary north-south line in the sky, known as the meridian, they could mark the exact moment of its transit. With two of these instruments operated in tandem, they could establish a local meridian and track the passage of time with remarkable accuracy, ensuring that temple ceremonies were performed at the correct celestial hour. For travelers and sailors far from any city, the solution was written in the constellations themselves. They learned to read the rotation of the circumpolar stars, those that never set but instead wheel endlessly around the North Star. The position of the Big Dipper or Cassiopeia, for example, could act like the hour hand on a great celestial clock. When the handle of the dipper pointed straight down, it might signal midnight in one season, while the same position weeks later would indicate a completely different hour. This was not a static skill. It was a dynamic mental calculation that required a deep understanding of how this stellar clock shifted with the seasons. A navigator had to know not only the date but also how to adjust the reading for the slow, annual dance of the night sky. This knowledge turned every clear night into a reliable timepiece, guiding ships across the Mediterranean and caravans through the desert darkness. The creation of these star clock systems reveals a layer of astronomical application that was deeply woven into the fabric of daily and nightly life. It was one thing to predict an eclipse years in advance, but quite another to know on any given night exactly what time it was by a single glance upward. This mastery of celestial timekeeping demonstrates that ancient astronomy was not solely about grand prophecies or aligning temples. It was also about the practical, essential human need to measure and organize the very flow of time itself, using the most constant reference our ancestors had, the eternal stars. Behind every precise prediction of a planet's path or an eclipse's timing lay an invisible architecture of numbers. The great monuments and mechanical devices were merely the outward expression of a deep and sophisticated mathematical genius. To quantify the cosmos, ancient astronomers had to invent entirely new forms of calculation. The Greeks, with their love for geometry, saw the sky as a series of triangles. The astronomer Hipparchus, working in the 2nd century BC, needed a way to measure the distances between celestial bodies. He developed a revolutionary concept, the chord table. Imagine a triangle drawn inside a circle, which represented his model of the celestial sphere. The chord was a line connecting 2 points on the circle's circumference, and its length changed based on the angle at the center. Hipparchus painstakingly calculated the lengths of these chords for a whole series of angles, creating a lookup table that functioned almost exactly like a modern trigonometric function. With this table, he could transform angular measurements taken from the Earth into concrete distances across his model of the heavens, bringing a new mathematical rigor to the study of the stars. This was a form of trigonometry born from the direct need to map the sky. Meanwhile, far to the east, Babylonian astronomers were approaching the same problems with a different mathematical language. Their system was based on the number 60, a choice whose legacy we still see in our 60 seconds in a minute and 60 minutes in an hour. This base 60, or sexagesimal, system was remarkably powerful for handling fractions, allowing them to perform complex algebraic calculations with an ease that would have been cumbersome with other number systems. They used these techniques to develop mathematical functions that modeled the changing speed of the moon and planets, predicting when a celestial body would slow, stop, and begin its perplexing retrograde loop. Their clay tablets are filled with step-by-step procedures, essentially early algorithms for solving specific astronomical problems. In India, mathematicians took the next logical step, moving from chords to the even more versatile sine function. They created detailed sine tables that allowed for more efficient calculations of planetary positions and the rising and setting times of stars. What is truly remarkable is that these mathematical breakthroughs occurred in cultures separated by vast continents, yet all converged on similar solutions to the same celestial puzzles. This shared intellectual journey reveals that the drive to understand the universe through mathematics is a fundamental human impulse. These were not just abstract exercises, they were the essential tools that turned raw observation into reliable prediction. By creating these mathematical frameworks, our ancestors built the first predictive models of the cosmos, systems that could be tested, refined, and trusted. The ability to calculate a planet's future position with a clay tablet and a handful of numerical rules represents a level of technical achievement we often mistakenly reserve for the modern era. It forces us to ask what other layers of their scientific understanding have faded from view, leaving only the silent stones behind. The true mastery of eclipse prediction lay in weaving together multiple celestial rhythms. While the 18-year Saros cycle was a powerful tool, ancient astronomers discovered it was not the only rhythm governing the darkness of the sun and moon. The Babylonians, in their relentless pursuit of precision, identified another crucial period known as the equinox cycle. This cycle spans 358 lunar months, and it provided a complementary key to the eclipse puzzle. Where the Saros cycle excelled at predicting eclipses of a similar type and visibility, the equinox cycle helped astronomers understand the longer-term patterns of when eclipse seasons would occur. By observing and recording these overlapping cycles for centuries, they could cross-reference them, creating a robust and redundant predictive system. Their clay tablets reveal not just raw data, but intricate computational procedures that combine these cycles to refine their forecasts, filtering out false alarms and confirming true events with ever greater certainty. This was no longer simple pattern recognition. It was an early form of mathematical modeling, a systematic approach to taming celestial chaos. Far across the world, Chinese astronomical bureaus were engaged in a similar grand project. Their scholars developed elaborate systems that factored in the moon's complex orbital behavior. They understood that the moon's path around the Earth is not a perfect circle, and its speed is not constant. Their predictive methods accounted for these subtle irregularities, applying corrective calculations to their eclipse tables to account for the moon's shifting velocity and distance. This allowed them to forecast not only if an eclipse would occur, but also its magnitude, duration, and precise timing. This work was considered a sacred duty to the emperor, as an accurately predicted eclipse demonstrated harmony with the cosmos, while a failure could be interpreted as a loss of heavenly favor. In the humid jungles of Mesoamerica, Maya astronomer priests encoded their own profound understanding into painted bark paper books known as codices. The Dresden Codex contains a famous Venus table, but it also includes sophisticated eclipse warning tables. These tables track the intervals between possible eclipse seasons, focusing on the 6-month period when the Sun, Earth, and Moon are aligned in a way that makes an eclipse possible. By carefully counting forward these warning intervals, a Maya priest could identify the specific days when an eclipse was a genuine threat. Their system was so finely tuned it could distinguish between a lunar and a solar eclipse, allowing them to prepare for the specific omen each event represented. The very existence of these advanced tables points to a monumental, multi-generational effort. It required the organizational capacity to maintain unbroken astronomical records for centuries, with each generation of priests adding their observations to a growing archive of celestial data. This long-term commitment transformed astronomy from a seasonal practice into a cumulative science. The development of multiple, overlapping predictive cycles represents one of the most sophisticated intellectual achievements of the ancient world. It marks the moment when humanity moved beyond watching the sky's patterns to actively modeling its hidden machinery, a quiet revolution in thought that laid the groundwork for all of modern science. What does it say about our species that we invested such immense effort over so many lifetimes, not for immediate gain, but to solve a puzzle whose answer would benefit generations yet unborn? This celestial knowledge was never meant to be kept in one place. It flowed along the same paths as spices, silk, and precious metals, a silent trade in ideas that connected distant civilizations. The meticulous eclipse records of Babylonian priests, inscribed on clay tablets, found their way into the hands of Greek scholars in Alexandria. These Greek astronomers, armed with a passion for geometry, eagerly absorbed the centuries of observational data from Mesopotamia, merging it with their own models of crystalline spheres. They did not see this as borrowing, but as building upon a common human inheritance. A few centuries later, when learning declined in parts of Europe, it was Islamic scholars in Baghdad and Damascus who became the new guardians of this accumulated wisdom. They translated countless Greek and Sanskrit texts into Arabic, preserving works that would have otherwise been lost to time. But they did more than just preserve, they refined. They corrected star catalogues, built more precise observatories, and developed the advanced spherical trigonometry needed to calculate the direction to Mecca from anywhere in the Islamic world. The most revolutionary idea to travel these routes was not a star chart but a concept. It journeyed from the mathematicians of India, where the idea of zero as a placeholder had been developed, through the Arab world and finally into Europe. This seemingly simple symbol, the concept of nothingness, transformed mathematical astronomy. It allowed for a place value system that made complex calculations, like predicting planetary positions, infinitely more efficient and less prone to error. This was not a story of one culture inventing astronomy, but of a great interconnected conversation that spanned continents and eras. A Babylonian observation could inform a Greek theory, which would be preserved and expanded by an Islamic scholar, using mathematical tools from India, and eventually spark a revolution in European thought. The shared human drive to understand the cosmos created the world's first global scientific network, long before the word global had any meaning. How many other threads of this ancient conversation have we yet to rediscover, and what might they tell us about our own search for unity in the universe? A mountain peak could become a perfect astronomical instrument. Across the Americas, ancient cultures mastered a form of celestial observation that did not require moving a single stone. They learned to read the sky by watching how it interacted with the land itself, creating what we now call horizon calendars. In the high deserts of the American Southwest, the ancestral pueblones of Choco Canyon engineered a landscape of precision. They constructed massive stone structures like the Great Kiva at Casa Rinconada with precise alignments, but their most remarkable achievement was tracking the moon's most subtle dance, the lunar standstill. Every 18.6 years, the moon reaches the extreme limits of its rising and setting points on the horizon, a cycle far more complex than the sun's annual journey. The builders of Choco designed features, including a spiral petroglyph known as the sun dagger, that captured these extreme lunar positions, marking a cycle that unfolds over a human generation. This was long-term planning on a grand scale, a celestial clock built directly into the canyon walls. Far to the south, in the Andes, other cultures used the natural architecture of their world. They selected specific mountain peaks and notches along the horizon as permanent sighting points. On the day of the June solstice, watchers would gather at a designated platform to see the sun set directly into a precise V-shaped gap between two distant summits. This moment, when the sun appeared to touch the Earth at a specific point known only to them, confirmed the turning of the year with unwavering accuracy. The entire system was a collaboration between the immutable sky and the familiar local landscape. This approach required a profoundly intimate knowledge of place. An astronomer had to know not just the cycles of the sun and moon, but also how those cycles played out against their own unique horizon. They had to memorize which ridgeline signaled the equinox, which peak heralded the coming of the rainy season, and which canyon alignment marked the winter solstice sunset. This knowledge was not portable, it was rooted, passed down through generations who lived in and learned from that specific valley or plateau. What does this tell us about their relationship with the world around them? They saw the cosmos not as a distant, abstract sphere, but as an intimate partner to the Earth, its events framed by the very mountains they called home. This versatile, landscape-based astronomy shows us that there was no single path to celestial knowledge. From the open plains to the deepest canyons, our ancestors proved that understanding could be found wherever a patient observer learned to read the dialogue between the heavens and the earth. The rhythm of the moon and the sun were constantly at odds, a celestial disagreement that threatened to disrupt the very order of human society. A lunar month is roughly 29.5 days, while a solar year is 365.25. These two cycles simply do not divide evenly, creating a profound challenge for any culture trying to build a reliable calendar. A system based purely on the moon would see its months drift steadily through the seasons, with a spring festival eventually falling in the dead of winter. To harmonize these two great cosmic clocks, ancient astronomers had to become masterful timekeepers, inventing mathematical solutions of breathtaking elegance. The Babylonians perfected what is known as a lunisolar calendar. They followed 12 lunar months, but this left them about 11 days short of the solar year. Their brilliant fix was to add an extra month, an intercalary month, at carefully calculated intervals. This was not a random decision. Their astronomers had determined that over a cycle of 19 years, the moon and sun would realign almost perfectly. So, 7 times within that 19-year period, they would insert a 13th month, keeping their lunar festivals in step with the agricultural seasons. This 19-year cycle became a cornerstone of timekeeping, adopted later by the Greeks and even influencing the Hebrew calendar. Meanwhile, along the Nile, the Egyptians took a radically different approach. They observed that the star Sirius rose with the sun each year just before the river's life-giving flood. They used this event to define a solar year of 365 days, dividing it into 12 months of 30 days each, plus 5 extra days added at the year's end. This civil calendar was beautifully simple and consistent, but it lacked a leap year. With each passing year, it drifted about 1/4 of a day against the true solar year, meaning their calendar slowly marched through the seasons, completing a full cycle every 1,460 years. Yet its stability made it a powerful tool for administration, and its basic structure was later adopted by the Romans as the Julian calendar. In the Americas, the Maya wove these cycles into a far more intricate tapestry of time. They did not seek a single calendar, but instead ran multiple interlocking cycles simultaneously. Their 260-day sacred round interacted with the 365-day solar year, creating a larger 52-year cycle. On top of this, they tracked the 584-day cycle of Venus and complex lunar cycles, all synchronized in elaborate tables. For the Maya, a date was not just a point on a line. It was a unique confluence of these spinning cycles, each carrying its own spiritual meaning and destiny. The creation of these systems was one of the most practical and vital applications of celestial knowledge. A functioning calendar told a farmer when to sow his seeds, a priest when to conduct a ceremony, and a king when to collect taxes. It was the framework that organized society itself, a testament to the human need to impose order on the flow of time, using the predictable motions of the heavens as our ultimate guide. Venus held a singular fascination, its brilliant light demanding attention as it switched roles from evening to morning star. This celestial dance was not just beautiful, it was predictable, and ancient astronomers in 2 very different parts of the world dedicated themselves to capturing its precise rhythm. In the rainforests of the Maya, this knowledge was preserved in the Dresden Codex, a bark paper book filled with intricate tables. These were not simple charts, they were computational masterpieces that tracked the movements of Venus over a span of 104 years. They accurately predicted its appearances and disappearances, accounting for the planet's 584-day synodic period, the time it takes to return to the same position relative to the Sun from our earthly viewpoint. The Maya understood a beautiful celestial harmony that 5 of these Venus cycles almost perfectly equal 8 solar years. This long-term accuracy reveals generations of unbroken observation, a scientific legacy passed down through priestly lineages. 1,000 years earlier and halfway across the world, Babylonian scribes were engaged in the same meticulous work. Their Venus tablets, dating from the reign of King Ammisajuka, carefully recorded the planet's movements as omens. A rising Venus might foretell a good harvest, while a disappearing one could signal conflict. These records, inscribed in cuneiform on clay, show a civilization equally obsessed with Venus's pattern, proving a long-term dedication to planetary science. This shared focus on one planet highlights a key characteristic of ancient astronomy, a selective but incredibly deep investigation. Instead of trying to map everything at once, they focused their intellectual resources on a few key celestial players, mastering their cycles completely. For both the Maya and the Babylonians, Venus was more than a point of light. It was a powerful deity. To predict its behavior was to understand the mood of a god, to know when it was auspicious to crown a new king or to send an army into battle. This blending of precise calculation with profound cultural meaning gave their astronomy a powerful urgency. The ability to look at the sky and know exactly when Venus would next emerge as the morning star was a form of magic rooted in mathematics, a secret knowledge that connected the rhythms of the gods to the fate of humanity. These silent stones hold a secret language of celestial alignment, a code we are only now learning to read through the field of archaeoastronomy. This discipline merges the digging of archaeology with the calculations of astronomy to understand how ancient builders intentionally wove the cosmos into their architecture. Take the Intihuatana stone at Machu Picchu, perched high in the Andes. This exquisitely carved granite pillar was far more than a ritual object. Its precise angles and surfaces were engineered to function as a solar clock and calendar. On the equinoxes, the sun would crown the pillar with no shadow at all, a moment of perfect balance between light and dark that marked a pivotal point in the agricultural and ceremonial year. It was a permanent, unmoving instrument that captured the sun's journey in solid rock. Across the Atlantic, the sprawling stone rows of Karnak in France present a different kind of puzzle. Thousands of megaliths stretch for miles across the landscape, arranged in long, parallel lines. Their purpose remained a mystery for centuries until archaeoastronomers discovered their grand design. The entire complex is oriented to frame the rising sun at the summer solstice, and key sightlines also target the moon's most extreme rising points during its 18.6-year standstill cycle. These were not random placements. They formed a vast, open-air observatory, allowing priests or astronomers to track the slow, majestic swing of celestial bodies across the horizon over many generations. The true genius of these sites lies in their seamless integration of function and belief. The Intihuatana, often called a hitching post for the sun, was designed to literally hold the sun in place at its turning points, a ritual act of cosmic stability that was also a precise scientific measurement. At Karnak, the sheer scale of the construction suggests it was a sacred landscape, a place where the community could witness the power of the heavens directly influencing their world. Decoding these alignments requires more than just taking measurements with modern tools. It demands a deep understanding of the cultural context. What did the solstice mean to the Inca, or the lunar standstill to the builders of Karnak? Was it about divine power, agricultural timing, or the very order of the universe? By asking these questions, archaeoastronomy reveals a layer of sophistication we never knew existed. These structures were not just aligned with the stars, they were conversations with the cosmos, written in stone for us to finally decipher. What other celestial conversations are still waiting to be heard in the ancient ruins scattered across our world? But to track the subtle drift of the heavens, you need a fixed and detailed map. This was the ultimate purpose of the star catalogue, a methodical inventory of the night sky that transformed astronomy from observation into a precise, data-driven science. The Greek astronomer Hipparchus is often credited with creating one of the first major catalogues around 134 BCE. Though his original work is lost, we know from later writings that it likely charted the positions and brightness of roughly 850 stars. He did not just list them, he assigned each one a coordinate based on a celestial grid of longitude and latitude, a system that allowed any other observer to locate that exact point of light. This was a revolutionary step, creating a permanent snapshot of the sky against which future changes could be measured. It was by comparing his own observations with even older records that Hipparchus made his most profound discovery, the slow wobble of Earth's axis known as precession, a cycle that takes 26,000 years to complete. Half a world away, Chinese astronomical bureaus were engaged in a parallel project, but they organized the cosmos through a different lens. Their star maps divided the sky into constellations that mirrored their own imperial court, with stars representing emperors, ministers, palaces, and marketplaces. This was not just myth-making, it was a sophisticated filing system that helped astronomers systematically track the movements of planets and the sudden appearance of guest stars, what we now call nova and supernova. Their meticulous records of such an event in the year 1054 provided modern astronomers with the data to identify the Crab Nebula as its remnant. The creation of these catalogues was a monumental logistical feat. It required standardized observation protocols, reliable instruments like the Armillary sphere for measuring angles, and a dedicated scribble class to painstakingly transcribe the data onto scrolls or clay tablets, ensuring its survival for future generations. This was science on a civilizational scale, a long-term investment in knowledge whose full value might not be realized for centuries. The very existence of these independent star mapping traditions in Greece, China, and Mesopotamia reveals a shared, global impulse to pin down the cosmos, to create a stable reference frame in a seemingly eternal but slowly shifting sky. What patience it must have taken to spend a lifetime measuring stars, not for immediate reward, but to contribute a single day to point to a puzzle that would take 1,000 years to solve. A civilization's relationship with the stars was profoundly shaped by the world it inhabited and the questions it needed the cosmos to answer. The Babylonians, surrounded by vast, open skies, developed astronomy into a form of high mathematics. Their primary concern was divining the will of the gods through planetary motions, which drove them to create incredibly precise computational tables. They could tell you exactly where Mars would be 6 months from Tuesday, not merely for scientific curiosity, but to advise their king on matters of war and peace. Their legacy was a predictive science rooted in numerical patterns, a celestial bureaucracy managed with clay tablets and sharpened reeds. Far to the east, the Chinese imperial courts viewed the heavens through a different lens. For them, the sky was a moral mirror reflecting the virtue of the emperor and the stability of his reign. A comet or an unexpected eclipse was not just a planetary event, it was a direct celestial omen. This belief fueled an unbroken tradition of meticulous record-keeping. Imperial astronomers maintained detailed logs for centuries, noting every irregularity as a potential critique from heaven. Their astronomy was less about predicting planetary positions and more about chronicling celestial events to guide statecraft and maintain cosmic harmony. A correctly interpreted omen could validate a dynasty, while a missed sign could be seen as a loss of the mandate of heaven. Across the Pacific, Maya astronomer priests wove the cosmos into the very fabric of time itself. They saw existence as an intricate tapestry of interlocking cycles. Their famous long count calendar measured vast eras, while their ritual calendar synchronized with the movements of Venus, a deity they associated with war and rain. For the Maya, predicting the reappearance of Venus was not an abstract calculation. It was knowing the mood of a god, determining the most auspicious day to crown a new ruler or to begin a military campaign. Their astronomy was inseparable from their spirituality, a complex system where celestial rhythms dictated the schedule of human ritual and destiny. Meanwhile, for the Polynesian voyagers, the stars were not gods or omens, but practical tools for survival. Their entire astronomical tradition was honed for one vital purpose: navigation across the trackless Pacific Ocean. They memorized the rising and setting points of hundreds of stars, creating a mental star compass that divided the horizon into directional houses. They understood how the zenith star changed with latitude, and they could read the faint glow of starlight on distant clouds to sense land far beyond the visible horizon. Their knowledge was an oral, living science passed down through generations, a system designed not to predict the future, but to find a way home in the present. These distinct paths reveal a beautiful truth about our ancestors. There was no single, linear progression of astronomical knowledge. Instead, each culture looked up and asked the questions that mattered most to its own survival, philosophy, and power. The Babylonians sought predictive control, the Chinese sought administrative warning, the Maya sought ritual timing, and the Polynesians sought physical direction. Their diverse approaches show us that the drive to understand the heavens is a universal human impulse, but the answers we find are always framed by the world we walk upon and the lives we lead beneath the sky. A simple stick planted in the earth could measure the vast dimensions of the cosmos. This was the gnomon, a vertical rod whose moving shadow became one of the most versatile instruments in the ancient world. Its principle was elegantly simple, yet the data it provided were anything but. By carefully tracking the length of the gnomon's shadow from sunrise to sunset, an astronomer could pinpoint the exact moment of local noon, when the sun reached its highest point and the shadow was at its shortest. But the true power of this tool was revealed over the course of a full year. The noon shadow would grow longer as winter approached and shorter as summer neared, with the longest and shortest shadows marking the solstices. Chinese astronomical bureaus elevated this practice to a high art. They constructed massive, precisely calibrated gnomons to determine the exact dates of the solstices and equinoxes, which were essential for maintaining their imperial calendar. The length of the shadow at noon on the summer solstice was a crucial data point, recorded year after year to detect any subtle shifts in the heavens. This systematic measurement provided them with a value for what we now call the obliquity of the ecliptic, the tilt of Earth's axis relative to its orbit around the Sun. How could a shadow reveal such a fundamental cosmic angle? It was geometry made tangible, a direct line from the ground at their feet to the center of the solar system. The Greek philosopher Eratosthenes took this shadow science to its logical extreme. He learned that in the city of Syene, on the day of the summer solstice, the sun stood directly overhead at noon, casting no shadow at the bottom of a deep well. On that same day in Alexandria, further north, a gnomon still cast a definite shadow. By measuring the angle of that shadow, he calculated the curvature of the Earth between the two cities. With this single angle and an estimate of the distance to Syene, he performed a feat of deduction that still inspires awe, calculating our planet's circumference to within a few % of its true value. He used a stick's shadow to measure the entire world. From setting market times to aligning temples, the gnomon's daily rhythm organized civic life. Its annual swing dictated the agricultural cycle, telling farmers when to prepare their fields and when to expect the returning rain. This humble tool demonstrates a profound truth about ancient science. It was not always about building colossal monuments or intricate gearwork. Sometimes the greatest discoveries came from learning to read the subtle patterns in something as ordinary as a shadow, proving that the keys to the universe were often hiding in plain sight, waiting for a curious mind to notice their quiet, daily dance. This celestial knowledge was far too precious to be lost with a single generation. Its survival required deliberate and sophisticated systems of preservation, methods as varied as the cultures that created them. For the Polynesian voyagers, the great star paths were held not in libraries but in memory. Master navigators underwent decades of rigorous training, learning to recite intricate chants that mapped the heavens. These chants were living databases encoding the rising and setting points of hundreds of stars, the seasonal shifts of constellations, and the subtle signs of distant islands. This oral tradition was a sacred trust, passed from teacher to student with meticulous accuracy, ensuring that the celestial map remained intact for voyages across thousands of miles of open ocean. In the great cities of Mesopotamia, they chose a different medium for eternity. Babylonian astronomers pressed their observations into soft clay tablets using a stylus. These cuneiform records, once baked hard in the sun or kilns, became virtually indestructible. Thousands have been unearthed, bearing precise numbers and dates for lunar eclipses, planetary positions, and mathematical procedures. This was knowledge built to last, a permanent archive that could be consulted, compared, and built upon by scholars centuries later. Their clay tablets were the hard drives of the ancient world, preserving a scientific legacy that has endured for millennia. Meanwhile, in the Maya world, astronomer priests recorded their wisdom in painted books known as codices. Made from beaten bark paper and folded like a screen, these codices contained elaborate tables for predicting the movements of Venus, the cycles of Mars, and the timing of eclipses. They were portable repositories of celestial science, blending calculation with ritual meaning. Tragically, the vast majority of these Maya books were destroyed during the period of European contact, a catastrophic loss that erased untold volumes of astronomical learning. The few that survive, like the Dresden Codex, offer us a precious glimpse into their computational genius. The very existence of these diverse methods, from memory chants to clay and bark paper, reveals a universal truth. Each culture employed the most durable technology available to them to safeguard what they deemed most vital. The survival of this knowledge against the ravages of time, climate, and even conflict stands as powerful testament to its profound importance. It was not merely academic. It was essential to navigation, to agriculture, to governance, and to understanding humanity's place within the cosmic order. What does it say about us that we have always been driven to record the sky, ensuring that those who came after would not have to start their journey of discovery in the dark? Imperial Chinese astronomers perfected a science of eclipse prediction that stretched across centuries, creating what we now call eclipse canons. These were not simple lists of events, but sophisticated systems of calculation and record-keeping maintained by state-sponsored astronomical bureaus. Texts like the Zhao by Suanjing contained complex mathematical methods that accounted for the moon's irregular orbit and the changing speeds of the sun and moon, factors that modern astronomy confirms are crucial for precise prediction. The imperial court's unwavering support for these astronomical bureaus created an unprecedented opportunity for long-term research. Generation after generation of court astronomers added their observations to a growing archive, each scholar building upon the work of his predecessors. This systematic, cumulative approach, sustained over hundreds of years, allowed them to refine their models and produce eclipse forecasts of stunning accuracy. Their success demonstrates how organizational stability and a clear, state-mandated purpose could foster a scientific tradition capable of tracking the heavens with meticulous, multi-generational patience. This deep integration of celestial observation into the structure of power reveals a world where understanding the sky was inseparable from governing the Earth. In fact, the very impulse to chart the stars so precisely often sprang from a source modern science has largely left behind: the belief that the heavens directly influenced human destiny. The clean line we draw today between astronomy and astrology simply did not exist for ancient scholars. In Babylon, the driving force behind their meticulous planetary records was the practice of divination. Priests scanned the sky for omens, believing that the conjunction of Jupiter and Saturn might foretell the fate of a king, or that an eclipse could signal a coming famine. This urgent need to read the divine will compel them to record planetary positions with incredible care, amassing the raw data that would later reveal the planet's underlying mathematical rhythms. Similarly, in the Hellenistic world, the rise of horoscopic astrology created a powerful demand for more accurate star catalogues and planetary tables. If you were to cast a meaningful horoscope for a newborn, you needed to know the exact positions of the planets at the moment of birth. This practical, if spiritually motivated, requirement stimulated immense advances in computational astronomy and the refinement of instruments like the astrolabe. The human desire to know one's fate, to seek meaning in the movements of the gods, became an unexpected engine for scientific discovery. It produced thousands of precise observations and sophisticated mathematical models that form the bedrock of our astronomical knowledge. This historical connection invites us to see ancient sky watchers in a more complete light. They were not primitive scientists held back by superstition, but holistic thinkers for whom the cosmos was a single, interconnected whole, where the physical motion of a planet and its perceived meaning were two sides of the same celestial coin. Their legacy challenges our categories, reminding us that the path to understanding the universe has been paved with many different kinds of questions. By observing a single star's silent passage, an Egyptian astronomer could command the night. Their most vital tool for this was the meridian, that invisible north-south line dividing the sky into perfect halves. When a bright star crossed this celestial midline, it reached its highest point, a moment known as transit. This was the most precise celestial tick of a nightly clock. To capture it, they used an instrument of beautiful simplicity, the Merkit. This device consisted of a plumb line, a weighted string that pointed straight down to Earth's center, and a narrow sighting bar. An astronomer or a pair working in tandem would align the sight with a chosen star, waiting patiently for the moment it crossed the plumb line's invisible extension into the heavens. That exact instant marked a fixed time reference, allowing them to track the passage of hours with a consistency that mechanical clocks would not achieve for millennia. But their genius did not stop at telling time. They noticed that as the weeks and months passed, the stars that crossed the meridian at a given hour slowly changed. A star that was high overhead at midnight in one season would be invisible months later, replaced by another. To systematize this slow dance, they identified 36 star groups known as decans. Each decan marked a specific 10-day period in the Egyptian civil calendar, rising just before the sun at the start of its assigned interval. Over the course of a single night, a sequence of 18 of these decanal stars would rise, effectively dividing the darkness into 18 equal hours. This created a star clock where the entire sky functioned as a single, predictable timepiece. The practical need for this precision was immense. It regulated the elaborate nightly rituals in the temples, ensuring that offerings were made to the gods at the correct celestial hour. For a society that believed the stars were the souls of the gods and the pharaohs, timing these ceremonies correctly was essential for maintaining cosmic order itself. Yet this sacred practice also yielded profound theoretical insight. By tracking these meridian transits year after year, they could measure the subtle drift of the decans, providing concrete evidence that the solar year was not exactly 365 days but slightly longer. This meticulous attention to the meridian reveals a civilization that saw time not as a simple cycle, but as a complex, multi-layered fabric woven from the predictable motions of countless stars. Their nightly vigil was more than timekeeping. It was a continuous conversation with a clockwork universe, one silent transit at a time. The very air they breathed and the ground beneath their feet shaped how ancient cultures saw the heavens. In the vast, rain-scarce deserts of Mesopotamia and Egypt, the atmosphere offered a perfect window to the cosmos. Night after night, the sky remained crystal clear, allowing priests to track the steady, predictable motions of planets with a level of detail impossible in cloudier lands. This relentless visibility invited a meticulous, data-driven science, where the primary goal was to log precise planetary positions and uncover the mathematical rules governing their dance. The environment itself fostered a tradition of relentless observation and record-keeping on clay tablets that could harden in the dry heat, preserving their calculations for millennia. Conversely, in the temperate, seasonal climates of Europe or parts of Asia, the pressing need was not planetary detail but seasonal timing. The success of the harvest, and thus the survival of the community, depended on knowing exactly when to plant and when to reap. This necessity drove the development of sophisticated calendrical astronomy focused on the sun's solstices and equinoxes. They built great stone circles to mark the sun's turning points, creating a reliable, stone-based almanac that could withstand generations of variable weather. Their science aimed at harmonizing human activity with the annual solar cycle. For cultures surrounded by ocean, like the Polynesians, the celestial challenge was one of space, not time. Their survival depended on successful navigation across thousands of miles of open water. Under the vast dome of the night sky, with no landmarks in sight, they developed an astronomy of stellar position and movement. They memorized the rising and setting points of hundreds of stars, creating a mental star compass that turned the entire heavens into a reliable guide. Their knowledge was practical, portable, and passed down through chance, a living science honed by the specific demands of their island world. This profound environmental influence reveals why astronomical traditions diverged so dramatically. A Babylonian priest would have been bewildered by a Polynesian navigator's star chants, just as the navigator might have found a stone circle marking the solstice, an interesting but largely landlocked concern. Each civilization looked upward and asked the questions most vital to their own survival in their specific corner of the Earth. The clear desert sky begged for planetary mathematics, the turning seasons demanded solar calendars, and the trackless ocean required stellar roadmaps. Their astronomy was a direct conversation with their environment, a brilliant adaptation that used the eternal stars to solve the immediate, earthly problems of food, travel, and time. How does the place we live still shape the questions we ask of the universe today? The moon's monthly journey was mapped against a backdrop of fixed stars, creating a celestial neighborhood of lunar mansions. Cultures as diverse as the Arab, Hindu, and Chinese all developed their own versions of this sidereal system, known as the Manazil, Nakshatras, and Zu. Each of these 27 or 28 mansions was a distinct group of stars that the moon would appear to visit on its path around the Earth, spending roughly one day in each before moving on. This was not a casual observation, but a highly structured method for dividing the sky into manageable segments, turning the starry expanse into a precise cosmic calendar. For a farmer in ancient India, the rising of a specific nakshatra just before dawn signaled the ideal time to sow a particular crop. For a Bedouin traveler in the Arabian desert, the appearance of a manazil on the horizon indicated the changing seasons and the timing of vital rains. These systems integrated the moon's cycle with the unchanging starscape, offering a reliable way to mark time that was independent of the sun. This sidereal tracking required generations of patient observation to note the subtle shift in the moon's position against the stars each night, a slow accumulation of data that eventually revealed its complete monthly circuit. The Chinese Zhou system was particularly elaborate, with each mansion possessing rich mythological and astrological associations that linked celestial events directly to the affairs of the imperial court. The precise moment the moon entered a certain zhu could be interpreted as an omen for state projects or military campaigns. This intricate weaving of astronomy, timekeeping, and cultural meaning shows a sophisticated understanding of celestial mechanics. By creating these comprehensive sidereal frameworks, ancient astronomers demonstrated a powerful desire to organize both space and time, to see the cosmos not as a random scattering of lights, but as a well-ordered map where every star and every lunar phase had its designated place and purpose. The celestial knowledge of antiquity did not vanish with the libraries of Alexandria. It was merely waiting, preserved in scattered manuscripts and translated texts, for a new age of discovery to unlock its secrets. When European scholars during the Renaissance began to rediscover these ancient works, a revolution was quietly kindled. The meticulous planetary records of the Babylonians, the geometric models of the Greeks, and the star catalogues of the Islamic world became the essential raw data for a new kind of science. These were not curiosities, they were foundational pillars. Tycho Brahe, the last great naked-eye astronomer, relied on the long-term accuracy of these ancient observations to confirm the precision of his own. He needed centuries of data to detect the subtle irregularities in planetary motion that his own lifetime of watching could not reveal. His assistant, Johannes Kepler, then used this vast inheritance, a celestial archive spanning millennia, to decipher the true elliptical paths of the planets, finally solving the mystery of their wandering loops. The ancient data provided the proof that the cosmos obeyed mathematical laws, laws that Kepler could then describe. This was not a rejection of the past, but a fulfillment of it. The predictive genius of the ancients reached its most dramatic conclusion with Edmund Halley. Delving into historical records from China, Babylon, and medieval Europe, he compiled observations of a brilliant comet seen repeatedly over 2,000 years. By connecting these ancient dots, he made his stunning deduction that these were not different comets, but periodic returns of a single object. His famous prediction of its return in 1758 was a triumph built directly upon the careful notes of scribes and court astronomers who had looked up in awe centuries before. The mathematical tools, too, were a direct inheritance. The Babylonian base 60 system survives in our minutes and seconds, the very units of time and angle that Kepler used in his calculations. The Greek development of trigonometry, born from the need to map the stars, provided the essential language for describing planetary orbits. This continuum of knowledge, sometimes fragmented but never fully broken, reveals a profound truth about scientific progress. It is not a series of isolated breakthroughs, but a great collaborative conversation across time. The legacy of those first sky watchers reminds us that every modern discovery stands upon the patient, collective work of countless generations who first learned to read the story written in the stars. Their achievements stand as a testament to human ingenuity, a profound legacy written not in textbooks but in the silent alignment of stones and the meticulous etchings on clay. These ancient astronomers, armed with nothing but patience and the naked eye, mapped cycles that unfold over lifetimes. They predicted the dance of planets and the darkening of suns with a precision that still commands our respect. This was not magic, but a science born of relentless observation and a deep, abiding need to find order in the cosmos. Their work demonstrates that the core of discovery lies not in the tools we hold, but in the questions we dare to ask across the centuries. Every civilization, from the Babylonians with their mathematical tables to the Maya with their interlocking calendars, added a unique thread to this growing tapestry of understanding. They prove that scientific progress is a collaborative conversation that spans generations, a slow and patient accumulation of insight where each culture builds upon the discoveries of those who came before. As we today peer into the depths of space with powerful telescopes and send probes to distant worlds, we are not leaving this legacy behind, we are honoring it. We are continuing that very same quest, driven by the same fundamental wonder that compelled a priest in Mesopotamia to track the path of Venus or an engineer in ancient Greece to build a universe of bronze gears. The next time you find yourself beneath a clear night sky, remember that you are participating in humanity's oldest scientific tradition. You are connected by that shared gaze to every curious soul who ever looked up and sought to decode the magnificent mystery of the